Okay, number 25 from the Segel book is asks you to calculate the pH of each species of phosphoric acid. So, talking about the phosphoric acid, it is a polyprotic acid. So it can protonate more than one time because it has 3 protons, right? So the first one from H3PO4 is will change to H2PO4 minus. And then HPO4 2 minus, and eventually lose all the proton and becoming PO4 3 minus. Each of these steps is happen at a certain pH, which refer to 3 different pKa. So the first pKa is 2.12, the second pKa is 7.21, and the last pKa is 12.32. So, question A, you need to calculate the pH of H3PO4, 0.2 molar. So, H3PO4 is a weak acid, right? And the first step, H3PO4 will change to H2PO4 and lose 1 proton. So 1 mole or 1 equivalent of H3PO4 may not protonate to 1 mole or 1 equivalent of proton because it's a weak acid. So talking about the weak acid, we need to consider using Ka to calculate the amount of proton that being dissociated from H3PO4. To using the Ka, you need to come up with the ICE table to understand how it works. So, initial, you start from 0.2 molar of H3PO4, and then when you let it protonate, the amount of proton is come out as X, as same as the amount of H2PO4 that being changed. And at equilibrium, because this X amount here is very, very, very small, so at equilibrium, we assume that the amount of H3PO4 is very minimally changed, and there's an X amount of H2PO4 minus form and X amount of proton. So Ka here will equal the concentration of the product, which is X from H2PO4 and X from proton times by multiply each other and then divide by the concentration of the substrate that being left. So in this case is 0.2 molar. You can also write minus X here and here too, but since we say that this amount is very, very small, so we can discard it. So to calculate using the pKa, so you need to change the pKa to Ka in order to use in these equations. Since the pKa for this is 2.12, so to change to Ka, you have to understand that pKa will equal to minus log Ka. So 2.12 will equal to minus log Ka, and Ka will equal 10 to the negative 2.12, which equal 7.58 times 10 to the negative 3. When you got the Ka value, you can plug into this equation and you can solve for x, which is equal 3.89 times 10 to the negative 2. So this x value also equal the concentration of the proton and the concentration of H2PO4 minus. To calculate the pH, you have two options here. So since we know the amount of proton that being dissociated from H3PO4, you can calculate the pH using the equation of pH equal minus log proton. And you can plug in this amount of proton directly to calculate the pH. Or you can also use the Henderson-Hasselbalch equation to calculate the pH. So Henderson-Hasselbalch equation is the pH equal pKa plus log B over A. So pH is what we want to know, and the pKa is 2.12. So talking about B and A here, so B would be referred to H2PO4 minus divided by the concentration of H3PO4 at equilibrium. So to plug in the concentration of H2PO4 minus is equal 3.89 times 10 to the negative 2, and then divide by the concentration of H3PO4 at equilibrium, which we say that it doesn't change much. So it's still equal 0.2 molar. So you can calculate the pH using these two alternative methods here. And the pH that you will get will be equal to 1.41 or approximately 1.41. You might also have questions that when H3PO4 change to H2PO4 minus, this H2PO4 minus also can change to HPO4 and eventually to PO4, 3 minus. But do those protons that dissociate at those steps will be affected in the overall pH here? The answer is no, because the majority of protons that being dissociated from H3PO4 will only come from the first step of dissociation. So we can omit the step of pKa2 and pKa3. So in summary, the pH for H3PO4 0.2 molar will be equal to 1.41.